I'm going to walk you through how to train one of these robots. We'll generate some training data by doing some examples of picking up this cube and putting it into the bowl. And then we'll see if the robot is able to pick up the cube on command by itself. The policy I'm going to train is called ACT, and the robot I'm going to train is called the SO-101. Now, this is the third video in a 4-part series. In the first part, I explained the trade-offs between building and buying your own robot and the options there. In the second part, I talked about some of the policies or models like ACT, GROOT, and Pi0. But today, I'm going to train the first of those models. It's the simplest one, called ACT, or Action Chunking Transformer. Now, I'm not going to show many slides today. I do recommend watching the previous 2 videos if you haven't already, because it's going to be a live demo. First of all, setting up the library called LeRobot from Hugging Face, then calibrating an SO-101 robot, which is this one here. I'll show you how to calibrate the robot, not calibrate the motors, because that's in part of the build step. Then I'll show you how to record data sets and some tips there. Then I'll show you how to train the model on a GPU. And then I'll show you how to evaluate whether the model has been properly trained and whether it's performing well. The scripts for today are going to be available to those who have subscribed or purchased the Advanced Robotics repo. You can find out more at trelis.com, trelis.com/advanced-robotics. And this repo will contain some guidance on building versus buying, some data preparation scripts and guide. And actually, that's no longer in draft form. It's up live. And the ACT training guide, the Action Chunking Transformer training guide that we're going to cover today. Now, there will be a follow-on piece in the series where I'll cover some pre-trained models like small GLA or GROOT or Pi0. So keep an eye out for that over the next weeks. So we're going to get started. And the library that we're going to use is called LeRobot. It's from Hugging Face. And we're going to start off by getting that library installed. So I'm here in the Advanced Robotics repo. I will, by the way, give instructions so you can follow along using the open source library from LeRobot. And then if you do have access to or decide to purchase access to the Trelis script, you'll be able to follow those as well. So I'll try to keep it somewhat broad. So here I am in Advanced Robotics. And the section I covered the last time was building versus buying a robot. Today I'm going to cover training. So we're going to move straight into the training folder here and check out the README that's in that folder. Now, things we need to do before we can do training is calibrate these robots and run what's called teleoperation, which means allowing this one here to follow the movements of this first one here. And when we're done with teleoperation, we'll move to creating data, and then we'll move to training. So the very first script, very first Markdown file we want to start up with is SO-101 teleop. So I'm going to go into that file, which is right here. And it's actually just called teleop, not even SO-101, because it will work in principle if you have different robots. So I'll just rename that there. And I'll go into teleop. So let's scroll up to the very top of the teleop file. And we're going to get started with installing LeRobot. Now, LeRobot is best operated in a Conda environment. Conda will manage your Python dependencies. It can manage a bit beyond Python. So to run LeRobot, it's recommended to have Conda. And getting Conda depends on what kind of operating system you have. If it's Mac OS with an ARM chip or with an Intel chip, or if it's or if it's with Linux or Windows. And you can look up with ChatGPT what the best way to install is. So what I've already done, I've done this on my computer, is I've downloaded the latest release. MiniForge is a common way to install Conda on Mac. It's actually a lightweight version of Conda that I think doesn't have licensing dependencies on Anaconda. So I have run through this and I've got Conda installed on my laptop here, which is a MacBook M4. Next, we're going to set up LeRobot, which is where we're going to clone. So I'm going to first move into the training directory, because this is where we're going to do everything for training. This is within Advanced Robotics. If you're not in Advanced Robotics, you can just clone it somewhere on your computer. And now I'm going to clone. Now, if you have access to Advanced Robotics, you can clone this specific version that I have developed and made some tweaks or improvements to. If you do not have access to that, you can clone LeRobot from Hugging Face or this specific commit, which I'll put in the description of the video below. So I've cloned LeRobot. You can see it here actually just on on the left-hand side of the screen. So I've got the LeRobot library here, and I'm going to now cd into that directory. So I'm going to change into that directory. So here I'll just do cd LeRobot. And now I'm going to create an environment, a Conda environment using Python 3.1 and then activate it. Now I've already created the environment, so I'll just activate the environment here, and you'll see using Conda, the name of it will appear to the left-hand side here. Now we're going to move through the installations. There are a few things to install. First, want to make sure we have FFmpeg, Conda Forge, and these packages here. And then we want to install all of the packages that are inside LeRobot here. And to do that, we will just run pip install -e and then dot. Now, if you want to speed it up a bit, you can first pip install UV and then do UV pip install instead of just pip install. I've already done that, so everything should be installed correctly. Now, there is one step where you might have to press Y in order to accept the installation, but after that, you should be all set with LeRobot installed here. So with LeRobot installed, we're now going to start to connect these robots up to our laptop. And to do that, we need to figure out what the mapping is to the USB ports. Now, I have connected them in through USB-C, which is the kind of smaller USB cable. And often you may not have enough ports because I've connected in 2 robots, so that's a USB-C each. I also have a camera here, which is pointing towards the setup. This is my front camera. And I have a camera on the robot, which is a wrist camera. So I've actually got 4 USB ports that I need to connect to. Plus, I'm also trying to record myself. So you may find that you need some kind of an adapter. I don't know if you can see it there, but I have this little USB extender that will allow you to plug multiple USBs into one single USB-C port right here. But anyway, what I said is we need to figure out which one of these ports is connected where. And to do that, we run find port. So if you just run find port here, it's going to ask you to remove the USB cable. So you want to trace where one of the USB cables is coming from. So on this robot here, I've got it coming into this cable here. So what I do is just pull this out. And once it's removed, I'll press enter. And now I'm going to reconnect it. And you can see here that it's printed on my screen, the motor bus. So this is the little snippet that I need because I need to give permissions. So I'll need to do this, grab this here, copy, paste it up here, which I think basically done. And then do the same for the other one. So I'll again run the port. This time I'm going to trace this robot, pull out the port, pull out the USB, stick it back in, press enter. Oh, I think I'm pressing on my keyboard, so I'm messing it up. Let's remove the USB. You can remove it from the robot either. That might actually be the best thing to do. And then press enter. And we've got the code for that. Okay, so I would want to copy this here, paste it here, and now run sudo. Oops. This is going to provide permission for using those ports. And I would put in my password. I've already done that earlier, so I think that's fine. But yeah, you should put in your password and then allow permission. Now, these identities here are what we're going to use to identify the motors going forward. Okay, so we've provided permission here. And next, we're going to move on to configuring the motors. Now, you don't need to configure the motors if you have pre-purchased the robots and they've already been configured. So mine were, I don't need to run this. If you are going to configure them, you'll need to pass in the robot type. This is referring to a preset configuration for the SO-101 follower and the SO-101 leader, and you need to pass in the port. So you'd want to run these scripts. If you run them, I can run them here. It's going to take you through each of the motors, so the gripper motor and then the other 5 motors, and allow you to configure them. I'm not going to do it though because I've already done it. So if you assembled your robot, you will want to go through this. So once your motors are configured, then you'll move down to calibrating the arms, which involves putting them into a middle position and then extending each of the motors to their full range of positions. So the top and the bottom of their position. Now, you can run this script here to calibrate them one by one. If you ever need to recalibrate, you should run this. And note that for the leader, you need to pass the port, and you also need to pass an ID that you're going to reuse then during training. And the same for the follower. You're going to need to pass the port and then an ID as well. Now, the first time you're doing this, you can actually just directly run teleoperation. And if you do that, it's going to force you to calibrate. So just a note on that. We will run the calibration. It won't require you to rerun it on teleoperation if you've done it once, but you could just directly run the teleoperation. So first thing it will do is ask you for the leader arm, which is this one, to put it into the middle of its range. And I like to put it into this position here. You could probably set another one, but I've got the L shape with this pointing down. I'll press enter. And now I need to extend it through the full range of motion. And you should actually see the numbers change, the min and max position. So here, this is the gripper. You should see the gripper positions change when I change that. The next one then is the twist. This is the wrist roll. So you should see the wrist roll positions, the min and max move. Yep. And then now the third joint. So you should see the min and max getting set. You should also see the min and max now on the fourth joint, which is the elbow flex. And now the shoulder lift is changing. And now last of all, we should see the shoulder pan, which is this one here. And with that, we should be done. So I think I've covered all the range of motion. Just make sure you have. And with that, we can press enter. Now we do the same for the follower. So you want to get this into a middle position with the gripper closed, press enter. Now check the gripper, min max, wrist roll. So I'm just making sure I cover it between the two stops. Now I want to get the wrist flex. I want to get the elbow flex, and I want to get the shoulder lift. So that should all be moving. You should see the numbers moving. And the last one then, of course, is the shoulder pan. So we should be setting the minimum and maximum there. Okay. So this is now back in position. It doesn't really matter if you don't bring it back to the same position, but we will. And the calibration is done. So we're ready now to move to teleoperation. And you can operate either with the cameras or without the cameras. Now we want to operate with the cameras, and we want to select our cameras. So rather than just running, we could run teleoperation like this. I'll actually just do it. No cameras will be displayed. And notice how the starting position with the gripper down is actually the camera on the side. And now my teleoperation should work. And I should be able to do things like pick up the cube here. Say, kind of hard to do from this position, but you get the picture. I can pick up the cube and I can teleoperate. But notice that there's nothing showing on my screen with respect to the cameras. So we want to now connect the cameras so we can view through the camera. So I'll just do Control Z to exit out. And now we're going to find the cameras using OpenCV. So we'll run Python. We'll run the Find Cameras OpenCV module. And I probably shouldn't have done that. And the reason is I'm trying to record as well on the cameras, which might cause issues. I did run it earlier so I could show you. And what this command does is it lists out the cameras here. And I have 4 cameras right now. And it also will take a screen capture. If you go to LeRobot and then outputs and captured images, it will show you each of the cameras. So this camera here, you can tell is this wrist camera. So I know now that number index 0 is the wrist camera. Index 1 is this front camera here. So that's index 1. We're just trying to figure out the indexes. Index 2 is the camera that you're looking at me through. And index 3 is my laptop's camera. So when we know all of the camera indices, we can now insert those into the command for running teleoperation. Notably, we can insert them right here at the bottom. I'll show you now. So robot cameras, this was missing when we previously teleoperated. We're going to define a wrist camera, OpenCV type at path 0, and we're going to specify the resolution here. You can do higher resolution. It may give better results, but it will be slower to inference and train. And then the frames per second. And then for the front, we run this here. So it's the very same command otherwise, except we're going to be able to see now with the cameras through rerun. Now there's one more note here. You might want to know, well, how do I know what configurations I can use for my camera in terms of the pixels? And for that, you can run an extra command. So let me see here. I've put together a little script right here. If you cd into the Trelis utils folder, I need to go back one into Trelis utils. So I'm in training, cd Trelis utils, and then I'm just going to run Python test camera resolutions. And hopefully this doesn't mess up my video recording either. But what it's doing is it's running through a checklist to see which resolutions are supported, because only if it's supported are you going to be able. So these are the default resolutions of the cameras, I believe. And then it's telling you which ones here are supported. So you can adjust it according to the needs. Probably there's not a whole lot of point going a lot higher. It depends on what the model supports. The ACT model does support higher resolution, so you could go to 1000 roughly in terms of pixel width. The small VLA model, I think, cuts them down to about 500. So there's not a whole lot of point in using larger resolutions. I like using smaller too because it's faster, especially the first time around. So we have information here on our cameras. We have input the correct specs. We got information which are supported by running a quick script. And with that, we're pretty much teleoperating. Now, I'm going to run this so you can see what it means. I need to cd into LeRobot. And you're going to see here on the screen now, my camera should appear. This is a good time, by the way, to adapt the position of this camera. So if you don't think that you're covering the full screen, this is a good position now a good time to kind of adapt this to give a good view. Now, you can see one thing that's bad is you never would want to record with me here because I'm currently in the view. So I would need to get out of the way. Also, my keyboard would need to get out of the way. Also, you want these objects to be in view. So this is kind of the setup you want. You want it to be clean. Arguably, this is maybe not great, the front camera. It would be better if I perhaps had a top camera that was looking down, because then it would just be a clean surface here. But yeah, this is the way I have it set up. So you can see some improvements would be possible there. Now you can also see the gripper camera here. Typically when we start, actually, we're going to start with each of the tests like this, just so we have this wrist camera in a more reasonable position. And there's one more thing I want to show you, which is you may notice that when you start operating, this is quite smooth here. Just listen to this. This is the part that tends to be not smooth. It's maybe a little jumpy. And there are two reasons why this can be jumpy. One is your PID controller, and the other is that your computer is not able to keep up basically with the information flow because you're sending a lot of image data. This is maybe jumping a little bit, but it's not terrible. It's not terrible. But I want to show you how you can tweak it using the PID controller if you want. To do that, you need to edit the P coefficient and possibly the D coefficient. So the P coefficient is what scales how quickly this robot follows. So you can see right now, yeah, it's definitely a bit jumpy here. If I move across like this, let me see. It's jumping across, which I don't particularly like. But if I lower it, what I can do is I can make it less responsive. So it will be slower to follow my lead robot, but it will also be less jumpy. So we can try a few things. The first thing I'll just show you is, let's just take away the robot cameras and see what that kind of teleop is like. So you can run, you can run by just, instead of running with display data equals true, you can just run with this simpler command here. So copy that and run teleoperation. So here we're not going to display data, which will lighten the load on my computer a little bit. Now let's see. So this is already smooth. You see that? So you can see how the effect of just displaying the data is causing it to jolt a little bit. Now, there's one other thing I want to show you, which is changing that P coefficient, which makes it less responsive. Lowering the D coefficient as well will also, if you lower it, it will have an effect. So let's go and check what those values are. They are controlled in a script. And let me just see where that script is. The easy way to find the script is actually just to search. So go to the search here. And now we want to go through. So here, you can see in SO-101 follower what the values of these coefficients are. So you can see for yourself. And as some recommended values, these are the defaults, but you could decide to make it more responsive or less responsive. So let's see if we can make it a lot lower responsive. I'm not recommending you do this, but let's just put it like that. And escape here. So let's just change the P value and rerun the script. And what I'm expecting here is when I move it across, it's going to be quite slow to follow. So I should be running here with no cameras. Yeah, look at that. So my robot is way over here. But it's way behind. So I'll move over here and it's just delayed. And this is not bad. It's actually fine if you very slowly operate. It's just, this is so slow, it's going to be impossible for me. Well, not impossible, but it's going to be harder for me to grip that. It's just going to be annoying. Like if I try to grip this cube, it's going to be so slow to kind of move that it's going to be hard to control. I'm already struggling here. So this is not really pleasant for operating. So I'm going to go back and change that. And let's put it to a really high value this time. Let's put it up to 32. And what we expect now is that it's going to be super responsive, but it's probably going to jump like this because it's kind of being forced to adapt really quickly. And now we have the jitter again, you see that? So this is also annoying to operate, not because it's not responsive, it's extremely responsive, but because precise motion, it's going to cause it to kind of jump around. So let's just go back to what we had. Save it at 8. And we'll teleoperate like this. And yeah, I mean, this should be the easiest way for us to run the robot. Yeah. And so you can see it's pretty responsive. I've got reasonable control. This is not like a great direction for me to figuring out where to go. We'll talk a bit about how you should actually save some training data. But you can see this is how you control the PID parameter. If you wish, in the Trelis implementation of LeRobot, you can just pass a parameter to control. So you can just pass in this coefficient here, or you can pass in a different coefficient in the command when you teleoperate. So just by putting in this here, you could swap it to some other value like 10 or whatever you feel the need is. So this is it. We're set up and we're running with teleoperation, which is great. I'm going to put the robot back in a start position and also realize that anytime I want to bring the robot back, it's a good idea to bring it back here. Last of all, you should probably just do a check displaying the data. We already did this, but just to make sure, I'll run here and I'm going to make sure that everything is within view of the robot. So we're in a good position. So rerun should come up here. Go across to rerun, just check everything is, in a good position. We're happy with the bowl. Also the front camera here, you could argue it's going to miss. Like I don't want to go way up because if I go here, there's no feedback. So that's kind of bad. You could also argue like this lead here, maybe you don't want to see it. Maybe it's best if you kind of put it there. So a few different things. But broadly speaking, we're ready now. I'm going to close rerun. I will stop running the teleoperation. And now we should be ready to train the ACT model. So for training, we're already within this training folder, and we have LeRobot cloned, and we're going to move to the train act. If you wanted to train another model like small VLA, which is probably the one I'll make a next video on, I'm working on this script now, but we're going to focus on train act, which is a very simple model, and we're going to train it from scratch, and I'm going to walk you through those steps now. Before we start though, something you should know about the act model is that it's not a pre-trained model, so you literally are training it from scratch. It also is not able to handle well multiple styles or modes. I talked a lot about this in the second video, but basically you need to first of all create a piece of data or a rollout or an episode for every single thing you want it to do. You need to have covered all of the various positions of, say, the bowl or the cube, because ACT works essentially through overfitting. It will just replicate what's in the training. It will not generalize very well. By contrast, some of the pre-trained models have seen a lot of data, and they will generalize more easily if you just have a few rows of data. Also, what I meant there when I said ACT doesn't support multiple styles or tasks well, you might get away with picking up the blue cube and putting it here, but it could start to struggle if you get it to maybe move the cube as a different task. And it may even run into issues if you try to run with different bowl positions, just because it's really designed only for a single task. And that's because of the continuous motor positions that it produces rather than a tokenized representation or a diffusion type representation, which allows it to capture multiple tasks in a better way. So for more on that, take a look at the second video, but just to caveat that ACT will basically average across the data that you show it, and it's going to be limited in terms of generalization, but it is lightweight. It's a very small model and it runs pretty fast. So here we are with ACT. We're not going to be able to evaluate the model without training it because it's trained from scratch. So there is no model when we start off. So the first thing we need to do is we need to train. But if we're going to train, we need to have some data. So we're actually going to first generate some data and then come back to training. So we'll move over to the data preparation here, and I'm going to show you how to record some data. I've recorded more rows. I've recorded like 16, and I'll show you how that performs. You probably want to record 50 if you want better performance. But I'm going to show you live how to record 1 or 2 rows, and then I'll also show you how to replay the recordings so that you can check that they're of high quality. So to start off, you're in the LeRobot folder. You want to log into Hugging Face with Hugging Face CLI login. If you ever want to know whether you're logged in, what you can do is Hugging Face -CLI and then who am I? And it tells me here I'm logged in, I'm running McGovern and I've got access to Trelis. So I've already logged in, and you could also set your user like this, which is just setting a variable that we're going to use later in the scripts. Now, before I run the data collection script, let me just explain high level. We're going to collect this time 2 samples. You'll want to collect 50. And I want to show you how you can record those 2 samples, but also how you can add more samples onto it. I'll also explain how you can stop recording midway. And I'll also explain how if you mess up an episode, you can go back and just record over it. So we're going to run this script here, LeRobot.record. We're going to pass in the follower details. We're going to pass in the leader details. We'll pass in the cameras, which there are 2, the wrist camera and then the front camera here. We will pass in then the display data equals true so we can see the cameras. That's going to be important actually. And we'll pass in the name of the repo that we want to push on Hugging Face. So when this is done, it's going to push the data set up to Trelis /SO-101 act-test. This is the number of episodes we want to record. This is the string giving the command, put the blue cube in the orange bowl. Technically, it probably doesn't matter what you use for this string because you're only going to train for 1 task, but it makes sense just to keep it consistent with what the task actually is. It really does matter, by the way, what you put there if you're training more general pre-trained robot. Then we'll put in a dataset reset time. It just allows for a little gap between each episode. And last of all, there are these 2 parameters here, which are actually going to comment out because we are not resuming a prior dataset recording. We are starting from scratch. And if we were resuming, we would need to pass in the address pointing to that dataset. But since we're not going to pass that in. Okay, so we're going to run this. It'll kind of happen quickly. So just note that when I'm recording an episode, if I'm done early, which is before the default 30-second cutoff, I'll press on the right arrow to move to the next episode. If I mess up the episode, I'm going to press the left arrow, which is going to reset. You'll see me do that. And if I wanted to stop midway, say I've recorded one episode and I'm done, even though I've set it to 2, I'll press escape. And that will allow me to neatly escape the loop, save the episode instead of rather throwing it away. So I'm going to show you how to record. We'll record 2, and then we're going to try and add 2 more on top of that. So let me just include this remove command because I have previously recorded a data set with this name. So I need to remove it. So we're starting fresh. And we should be up and recording soon. Okay. Recording episode 0. Now, I should get out of the way so I'm not in the camera. Notice that I see my arm is still in the camera on the screen here. I've moved this just to be pointing the same way, so it's a bit easier for me to teleoperate. The key thing here is you should not be looking at this setup. You should only be looking at the cameras because that's all that the robot will have access to. So if you start looking at this, it's kind of cheating. Now, I've clearly messed up this episode, so I'm going to press the left arrow. Reset the environment. Now, there's going to be some shadow here just for this demo. So I don't recommend, like you can see shadow in the image, but I'm going to do it anyway. So now, looking at the screen here, I'm going to move across. I'm going to try pick it up. Close. And put it down here. And this is actually not a terrible episode. I'm fairly smooth, and I'm bringing it back to a position here. Okay. So now I'll press right arrow to accept. Reset the environment. So I've got to put the cube back in position. Ideally, I really should be putting it in the same position. Now, I should be consistent as to when I open the gripper. I like to open it right at the start. There is a little delay here before the next episode because it's loading. Recording episode 1, it's 0 indexing, so 1 is actually the second episode. What I like in the actual data set I recorded is to open the gripper at the start to make that really consistent. It's bad that I hit off the bowl there, so I should really re-record. My gripper really wasn't wide enough as well, so this episode I don't like. Okay, I just don't like this. I don't like this. I'm going to restart. I wasn't even. Okay, so let's lift it up, open the gripper wide. That's maybe a bit wide because I'm out of view of the wrist camera. Move across here. Move down. Grab. So not a terrible episode, not really up to standard, I would say. I would probably re-record this, but for the sake of demonstration, I'm just going to leave it as is, press the right arrow. And that should actually summarize. That should complete the recording. And we'll see here on the screen that the data is being saved and it should be pushed up to Hugging Face. Stop recording, I'm hearing commands here. There's commands being told to me, and you can see the episodes now are being pushed up to Hugging Face. Episode 0 and 1, exiting. So we're done. Now, let's say I want to record one more episode. I'm going to resume. And this time, the number of episodes refers to the number I want to add. So if I want to append one, sorry, I'm in a bad position here. If I want to append one episode, I'm going to just copy this. Don't delete the folder because we're going to need those episodes. And now we're going to run with resume true and pointing to that folder. So let me get ready to record. Okay, so that was a mistake already. So I didn't reset the environment. Really, I should put a piece of tape here and try and mark the same spot. Now, on the other hand, if you put a piece of tape, that's going to be in the image. So you need to consider whether that might confuse the training. Okay, restart, reset the environment. It's not great. My keyboard is here. So ideally the keyboard should probably not be there. So I'm going to go up. I'm going to open. I'm going to go down here. Looking at both cameras on my screen, lifting it up, placing it in here. I kind of hit the bowl edge. Make sure you make the gripper go really wide there so it clearly lets go of it. And yeah, not a very consistent finish there. But I have my data now. I've pressed the right arrow. And the data set should be pushed up to hub. So we will have a data set that's now been pushed. And the next thing to do is just replay some of these episodes. So you want to manually inspect, well, I don't know about manually, but you want to check if each episode you've recorded is a valid one, which you can do by just copying this here. Dataset episode 0 means it should replay episode 0. And looks like I had an issue there. And the issue is because I did not give it, I gave it the wrong name. You need to point to the actual data set. The other thing you can do here, you can display data, which is not a bad idea actually, because if you do that, you can inspect whether the cameras are showing what you think they should be. Oh, actually, sorry, that's wrong. You cannot display data during the replay. So I guess you would have to look at the videos by opening them up maybe on Hugging Face and inspecting. All right, let's run this here. So this should be inspecting, it's replaying episode 0. And that did not look good. Oh, okay. But yeah, that's probably a bad thing. The fact that the first episode, the first part of that episode, it's kind of jittered. That's an indication you might want to delete that episode. Let's just replay it again in case it was unlucky. I don't think it was. I think there probably was some noise at the start. It's not terrible. I don't like that there's a big pause at the start of the episode. Too much of a pause might train the robot not to even move. Now, yeah, this is obviously not, it's not using the sensors. It's just literally replaying whatever I did as a motion, but it's useful to check the data quality was correct. So you want to go through and replay every episode that you recorded to make sure that the quality is good. When I later evaluate, you're going to find that replaying is also useful because you can replay an episode to figure out where the blue cube was, and then you can roll forward on the trained policy. And you should always be getting your trained positions correct. Anything that you train, if you replicate it exactly with the cameras and the cube position, it should definitely roll forward. If it doesn't, then you've got some kind of problem. Ideally, you will generalize a bit. So if your cube is a little bit off, it should still pick it up when you train the policy. That's going to be more difficult with ACT if you haven't covered that range of positions because it doesn't really generalize well. But you should always be able to at least have the model succeed on exactly replicating tasks from your training set. So this is the training. I'm going to move forward then to show you how to train the model on a GPU. Actually, you can train on your Mac. I might even run the training quickly on the Mac, just so you can see, but it will take quite a bit of time. And then we can take a look at training on a GPU, and then we're going to evaluate whether the model actually performed well. So we're done with data prep, and we're going to move to training. And the way you want to find the script is to go back into the training folder and find the README that's in there. And basically we've done teleop, we've done the data collection, and now we're going to move into the train-xxx.md script. That just means you should find the markdown file that's relevant to the type of model you want to train. And the one we want to train is the ACT model. There will be some other scripts or other markdown files with explainers that I'll include, like small VLA, which I'm working on right now. But this video is about ACT, so we're going to go back to the train ACT folder, markdown file rather, and we'll get started here on training. So we're going to train the model. I'll train it just on Mac first, which will be just a quick demo, but it is kind of slow if you train on Mac. So it's better to train on GPU. So I'll then train on GPU. And I'll show you the results that I got from training on a bit of a larger data set I recorded earlier with 16 rows, which is still on the lower side, but it's going to be good enough to actually get good evaluation results, at least on those specific training examples. So let's move on to train here. I do want to mention a few things before we start. I want to talk about a few of the key parameters that we'll need to set, and also talk about using an evaluation set. So if you've watched other videos on this channel around training language models, you'll know that I'm a big fan of not just having a training set, but also a validation set. And the validation set is not used to update the weights of the model, but we calculate the loss on the validation set during training. So we can see a training loss that's hopefully falling, but we can also see a validation loss that's falling. And the reason the validation loss is very useful is because when we see it plateau or indeed go up again, that means we've trained for long enough. So it helps you know how many steps you should be training for. If you don't have a validation loss, and for that you need to have validation set, there's not an easy way to know when you should stop training. There's not an easy way to know how many steps you should train for. So I've updated the scripts in the Trelis LeRobot implementation to include splitting off a validation set. And this is going to allow us then to track that validation loss and tell whether we've trained for enough steps or not. And quite simply, it takes 10% of the total training data and it splits that off as validation up to a maximum of 32 rows. So if you have a huge training set of say 1,000, it's still going to take a validation split of 32. Why is that? Because if you always took 10%, you can result in having a really slow evaluation every say 100 steps you're doing validation. If you have a big validation set, it's going to really slow down the run. So I cap it to 32 to be enough, but I make sure it's 10% or 32, whichever one of those is the largest, or rather, whichever one of those is the smallest. Now, the way that LeRobot works is it will predict future motor positions. So if you have a given set of images and motor positions, LeRobot, the ACT model, will predict forward the next default 50 positions for the motors. And we're at a frame rate of 30 frames per second. So if you predict forward 50, that's 1.66 seconds worth of frames that you're predicting forward. So this is the chunk size. And you can find this parameter here within the ACT configuration ACT file. So if we go down and we just even search here for chunk size, you're going to see that it's set to 50. Now, the observation steps, this is how often we are going to make use of the frames, and it's defaulted to 1. The library doesn't actually support changing this, I think, so you got to leave it that we're basically going to have every frame that's going to be used, at least for the purpose of training here. And then the last parameter here is the number of action steps. This is actually only relevant when we get to inference or evaluation. It's not relevant during training. During training, we will always predict 50 steps. During evaluation, we will still predict 50 steps, but we can decide to only use the first, say, 15 and then throw away the rest because we will predict a new 50 steps. And the reason you might do this is because you just want to take the closest predictions in time and then recalculate the next 50 rather than using the full 50, which might become unstable towards the end. But it is beneficial during training to have a decent kind of frontier predicted so that you pull in the knowledge from all those 50 steps. You could maybe make it larger to say 100. If you start making it even larger, then that's going to mean it takes more compute to do a forward pass. So there's some kind of optimum where you want to predict a reasonable number of steps so that you're not forced to rerun prediction too often, but you also don't want it to be too long of a horizon. So we're going to set this to 50 and 15. I think the default in LeRobot is higher, but the recommendation based on reading the paper is more in this range of, say, the 50 and then 10 to 15 for action steps. Okay, the other thing which is challenging to understand is around the KL weight. You really have to watch the previous video to understand how the ACT model works. But the ACT model, while it predicts forward, say, 50 steps, it also tries to predict what the style is. Style refers to different ways in which you could make the same movement. Often a clear example is if you're going around an obstacle, you can go around to the right or you can go around to the left. And this is a problem for the ACT model because it will average those two paths, and that can result in you just hitting the obstacles because the average of left and right is just going right through the obstacle. To avoid that, there's a specific encoder in the ACT model that comes before the main model, and it tries to build up a model of which style you are using during training based on actually seeing the actions. So actually seeing the future actions. And so because it's able to model the style, when you come to inference time, you lock it in so that it just uses one of those styles. Now, in practice, it's actually very difficult to accurately model the styles. And you may not even have multiple styles. In the examples I just recorded, I pretty much used a similar style for each of the rollouts. Now, you could maybe debate that. So there may not be any style differences to even measure, in which case this style encoder is not really going to do much. But the KL annealing and the KL weighting, just to come back to what this is, this affects, or it sets rather, the weighting of how much importance you want to give to this style model that comes before the main ACT model. So if you decide to put the KL weight very large, it's going to penalize putting any information in this style encoder, which means it's not really going to be used. If you set it to a lower value, it will encourage the model to actually capture the style. But if there's no style, it doesn't really matter what value you set the KL weight to. So that's actually what we're going to find. Even with my 16 rows of data, turns out there's not a whole lot of style differences to capture. So you could say I could have just run without using the encoder at all. Now, if you had a much larger data set, maybe 100, 200, and you do have different styles, maybe you'll start to see it pick up some style. And then it will be important to set this KL weight properly, because if you set it too high, then it's not going to allow any style information in the encoder. So you're going to run into this issue of collisions or just poor performance. And if you set it too low, well, then the model's kind of going to cheat by packing information into this style encoder that really should be in the main encoder. I know that's a lot to absorb. It'll help if you watch the second video. For now, my basic message is possibly if you have a small data, it won't matter what value you set the KL weight to because you just don't have a ton of style. If you do have different styles, you may need to rerun the training with different values of KL weight. You may also want to run with this fancier parameter that I have set up called KL weight annealing. What does KL weight annealing do? It will basically mean that at the start of training, your encoder is not being used, the style encoder, and it will gradually be brought online. And you can set at what point it comes online. So if we look at configuration ACT and we search KL annealing is turned off, if you turn it on, you can basically turn on this style encoder partway through training. It allows the model to kind of train itself a bit before the style encoder comes on. And you can decide when the ramp starts and when the ramp ends. So it's just going to ramp this on and then it's going to go. This is the KL weight here. You could possibly set it in the paper. I think it's recommended to set to 10. But if you have a relatively small amount of data and you do have styles, which you may not, then you probably want to set it to something lower. Because it's going to be kind of subtle capturing the styles. And if you set the KL weight this high, it's just going to penalize putting any information in the style encoder and there just won't be any information there. So I'm going to leave it as is. There's also a dropout parameter. This might remind you of the dropout within LoRa. This just means some weights are ignored on backward passes. And this allows you to help regularize or help avoid overfitting. So this is default. I wouldn't change it. I would just leave it as is. These training presets around the optimizer, I also would leave to the defaults that are recommended here. Okay, so we're going to run training. By the way, these configuration steps here, the action steps, chunk size, these are all specific to the model, the policy that we're choosing, which is ACT. If you are using a different model like small VLA, you will need a different set of parameters. And the parameters might be different because the model might not have any KL weight annealing. In fact, small VLA, Pi 0, also the Groot N1 or Groot N1.5, they just don't have this type of architecture. So they will have different parameters that I will talk about in different videos. On the other hand, the training script does have common parameters no matter what model you're training. We're going to take a check here. You can see we are able to pick the batch size. I would pick maybe something like 4. If you have got more data, like say you've 200 rows, then maybe pick 32 or 16. The larger the batch size, the larger the VRAM you need. So if you run out of memory, you might need to lower it. This is the total number of steps. We're just going to run for 600 steps here because I want to show you on Mac. It's going to be slow, so I don't want to wait for too long. And here's the evaluation frequency for that evaluation split of data that I've broken up. This is the logging frequency, can maybe make it a bit more frequent. And this is the saving frequency, how often you want to save the model. I'm only going to save it at the end, so I'm just going to put it at 600. So this will save a checkpoint. It'll also save it at the end, so this is probably redundant. I think maybe I can set it to none. Let's see if I get an error. But if I set it to the end step, it's going to save the model as a checkpoint, and it's going to save it at the end of the run, which is kind of redundant. Okay. This is if you want to resume a training, which we don't because we're training from scratch. And yeah, here's where I set that 10% of the data is going to be used for validation. And here's the cap where you can set it to a max of 32. These are default values, so if you don't pass these, they will be set anyway. All right, so we're going to run this here, and we're going to give our run a name. I'm just going to call it act test, actually. So I need to make sure my output directory, my job name is all aligned. Here, I will need to remove the folder if I'm trying to overwrite. This folder won't exist, so doing this won't do anything. And here I do need to update this upload command. So what am I doing here? I'm activating the environment. It's already active, actually. Setting my HF user. I'm setting the repo I want to push my trained model to at the end, setting the policy type, setting the output directory, the job name. We're not going to run a CUDA. If you just run this, it won't fail. It will just swap it to whatever device is available. We're going to run on Mac, so I'll run with MPS. You could also run with CPU here. We're going to run with weights and biases, so enabled. By the way, if you're running this the first time and you're not logged into weights and biases, it will prompt you. You'll have to click. Actually, it will prompt you, and you may not know what to do with the prompt. It's actually expecting a number. You should put in, I think, the number 1, which will then bring you to a link where you can get your API key from weights and biases. Weights and biases has got a fairly high usage threshold for free. It's quite expensive once you hit that threshold, but you can just delete stuff from your account. By default, weights and biases uploads the models, which takes up insane amounts of space. So if you just delete older runs, it will create up space pretty easily. Now, there's one more parameter here, which is called image transforms. This will add jitter to your images, which in principle is a good idea because it adds randomness. And this generalizes your model so that if there's changes in light, it can still work. But the problem is if you don't have a lot of data like I do, I'm running on 16 rows. Actually, I'm only running on 3 rows here. Just because we're doing a quick run. Then the jitter is going to make the results even worse because there's going to be so little data that it's not going to see the ground truth data in the training, and that's going to make your performance worse. So only set this to true if you have a large amount of data, like at least 100 examples. Once we've trained, I like putting this command right after because it will upload the model then to Hugging Face, and then we can start to, once it's up on Hugging Face, we can access it for running evaluation later. Okay, any other comments I have here before we run? 1,000 steps takes 5 to 10 minutes. I use 3 rows. Yeah. So if you're running 30,000 steps on a H100, it takes about 30 minutes. I'll show you how to do that in a moment. This is the upload command, which you've already got above. If you have any install issues on CUDA, this is relevant. We're not on CUDA, so this is not relevant. So with that, I think we can probably get started here. I'm actually just going to change this to be a bit less long, even though this is data workers. That should be fine. I've got this many CPU cores. So yeah, let's try this. Save checkpoint. I guess actually this is probably the way to turn off saving the checkpoints, because then no matter what I have here, I think this doesn't really matter. So even if I set this to 600, I don't think it matters if I've turned off saving the checkpoints. All right. So let's copy this and let's paste. And what's gone wrong? Yeah, and I think we're probably just in the wrong folder here. So you have to be careful because within LeRobot, there's a LeRobot folder, which, yeah, that can cause confusion because if you accidentally CD one extra folder deep, you're going to run into trouble. So I do need to CD into the first LeRobot, and then I need to run. Okay, so this is running. You can see I'm logged into weights and biases, so it's going to start up that run straight away. And we should... Okay, so we did get an issue here. And I think that might be to do with me setting the value of none right here. So I don't know if it likes this. So let's just rerun. All right. So we'll open that up. And if we scroll down, you will see this here. This is fine. We should soon see some logs starting to appear. So let's actually click on runs so I can see a history of my different runs. And this is the one we want to view. There's no data just yet, but we can compare it to some training that I would have run before. For example, like some of these tests here. And this is going to run on MPS. You can see it's printing out the number of frames in the data set. And by the way, this is relevant. So you can think of every frame as a data set, row. It is a data set row. And we're going to cycle through all those frames. So basically, if you have 30 frames per second and you have 30-second episodes, that's going to be 900 frames per episode. So you can then calculate how many total frames you have. And the way the trainer works is it's just going to sample through all of these frames. Now, you want to run a number of steps so that you have multiple epochs. Multiple epochs means you actually want to run training on every frame a few times, maybe 5 to 10 times. So whatever your number of frames, you probably want to have that times 5 number of epochs, number of total steps. Except your batch size is 4, so every step is actually covering 4 frames. So it would be something like 5 times 1500 is 7500, but then divided by 4 for batch size, which is very roughly back to about 2000 steps. Now, this is only for a very small number of frames because we've only got 3 episodes. So that's why 2000 steps sounds like a low number. But if you have, say, 50 rows of data, then you're going to want to have, something like 25,000 steps minimum. I think 100 is the default, but that's the logic for how you decide on how many steps you want to have. Okay, let's see if we're making any progress. Yeah, so here you can see our loss. The gradient norm is kind of high. You usually want this to be towards 1, but yeah, it's a very small amount of data. We should start to see the data appear now. Just going to hide that. Refresh. So yeah, let's hide this. Actually, there's no data showing yet on weights and biases. It should appear soon. We've just got 1 row calculated, and this is at step 50. And I think we'll start to see data appear around step 100. Okay, so now we've step 100, and you can see the loss has gone down a lot. So this is good. Maybe we have some training data showing at this point. Sometimes there can be a lag. Okay, yeah, so this is good. Training data is showing. We don't have the eval data yet, but we can see the training data is showing up here. What we're looking for is, to check that the loss here is falling. This is the total loss, which includes the L1 loss. This is the reconstruction loss. This is really what we care about. It's basically saying the predicted actions are matching the ground truth actions from our training data set. So we want this to be down towards 0. the loss here is combining this loss with the KL divergence loss, which is the loss from the style encoder. Now, if you do have multiple styles, you then want to be careful what your beta parameter is and see if you've got the right beta parameter. If there are multiple styles, you should see some KL loss, even as you move out towards high steps. What we're going to see here, and I'll show you on a larger data set, the KL loss is just going to go to 0 because basically there are no styles to encode. But if you truly have styles, you do not want it to go to 0 because you need the encoder to be capturing some information on the styles. And actually, you want the style vector, which is Z. This is kind of advanced what I'm saying here, but you want the style vector, which is called Z, to be non-zero. And you want each of the dimensions actually to be used. So you want a non-zero styles vector if there is a Z, and you can actually check here the percentage of the active dimensions. So I've added code to check how many dimensions of the Z vector are being used. This is going to go to 0 because there is no style. But if there was a style, you would not want this to go to 0. And if it was going to 0, you need to lower your KL weight, because lowering the KL weight will allow more information to be captured. So you can see this is going to 0. The loss here is going down, which is good. And pretty soon we should see the eval loss as well. So I'm going to just give this a second. I want to show you though what happens if you run on a much larger data set. And I'm going to show you data from running here on 16 different rows and running for quite a bit longer. As I said, because there's no style, basically, there are no active dimensions in the style vector. So the style vector is just zeros. There just is no style. And what I want to show you, you can see that's true both for the eval and for the training. So the style vector here as well for training is just going down to 0. But the loss is lowering down here, which is what we want. It's going all the way down to 0.11. And you can see here the L1 loss, it's going down to a pretty low value here. So this is an example of training for 10,000 steps on more data, 16 rows. And you can check then the validation loss. So here's the validation loss. You can see it's going down, not quite as aggressively. So you can see the validation loss is around 0.35, while the training loss is about 0.1. So there's definitely a gap. And this just tells you that your model is not generalizing particularly. I mean, it's generalizing okay, but it's not generalizing very well to the validation set. But this is nice because you can see here that already by about 10K steps, we're not getting a huge further reduction. And so you can probably decide to stop. In fact, based on the validation loss here, you probably could have stopped somewhere around 4,000 to 6,000 steps. Because even though the training loss goes down further, the validation loss does not really improve much more. So this is your heuristic for deciding when to stop or if you've used enough training steps. Now, this run here where I went for 10K steps and I used 16 rows, this is the run I'm going to use later in the video when I show you evaluation, when we try and evaluate the performance of the model. It's going to be the robot model that I have trained on this data here. All right, so let's go back and take a look at our quick map test. We can see the loss is still going down, but it's kind of hit an elbow. So the rate of improvement is now falling. Let's just quickly run here, see if, I think we'd only see a validation step emerge once we get to the 200 step point. You can see the active dimensions. Okay, it's bounced up a little bit, but I would not assign too much importance to that just yet. Okay, I'm going to let this run on the Mac. And in the meantime, I'm going to show you how to set up the training on a GPU. Let's actually go back now and do the very same thing, but we want to set it up on a GPU. So go back to Train Act. And if you scroll up, you should see there's a link for getting started here. If you want to run on a GPU, you could run on Colab. So you could put these scripts into Colab. You could run on RunPod. That's what I'm going to do using this one-click template here for a H100. Well, it's actually just a one-click template. You can pick any GPU. And this is an affiliate link, by the way. If you click in here, you, I just want to sign in. Let's see here. So I've got the one-click template. I'm going to pick a H100. You could pick something smaller and cheaper. I'm going to call it Act. And if you check the template, we're starting up with PyTorch CUDA, PyTorch 2.2, CUDA 12.1. And what's important here is we are going to, we're just going to accept this. We don't need a huge volume of disk, but I've put plenty of spare. Like this will be fine. Just run with 25 in this case. Set overrides and deploy on demand. And once this gets up and running, we're going to SSH into this and we're going to clone the repo so that we can start to run those scripts. So it's going to take a moment for that to start. We'll be able to get the SSH command. So I'm going to copy that, head back over to cursor. Training's still going here. We've got 250 steps. Connect to host. And we're going to want to add in a new SSH host. So I'll just paste it in here. And I do need to put in the right SSH key. The first time you do this, you'll need to go into RunPod settings and you'll need to add in a public key. So you need to get ChatGPT's help to add in an SSH public key. You want to create an SSH key in your .ssh folder that will have the private and public key. You take the public key, you put it into RunPod. Okay, open configuration. Now, in the meantime, it looks like I have hit a problem here on getting the model to push up to hub. And I know why that is. It's because I actually tried to be fancy and not save any final checkpoint. So you see, when I went into the training settings, I set that to false. I should have set it to true probably, just to save that final checkpoint. So if I'd have done this, it would have saved it. That's just because my upload command right now, when I run it here, it's looking to upload from this folder here. But actually, we didn't save checkpoints. We only saved the final model, or at least I hope we saved the final model. So when I look in the outputs here, train, and we're looking at act test, there are no checkpoints. So I think that was a mistake. I should have left this on to true to make sure that we do at least save. So what I'm going to do is just run this for a very small number of steps. Because when we run that upload command, it's looking in the folder for outputs, train, act, test, checkpoints. But of course, if we didn't save any checkpoints, that's going to be a problem. And it does say it should save after the last step, but it's not clear to me it is doing that. And it's possibly because I've turned off the saving. So let's just double check that. In the meantime, let's try connecting to the new host. The RunPod host we're connecting to is 157.66 and .11. So it's this one here. So you just connect in and we continue. Now, when this loads, we should have the option to clone a repo, which is what we want. Okay, so we clone a repository here. We're going to clone from GitHub, Trelis Research, Advanced Robotics. If you're not using the Trelis Research implementation, you can instead decide just to clone Hugging Face LeRobot. I like to clone it within the workspace folder. And this will give us an option now to open the folder, to open the cloned repo. And once this happens, we should be up and running. You got to trust the authors of the repo. Okay, so it looks like we're in good shape. We'll open up a terminal here. Just make the screen a bit bigger. And I need to CD into training. And once I'm in training, I do need to go through the installations. So I'm going to do this with you now. I need to go into the, not troubleshooting, but I need to go into Teleop here. And now I need to go down to the Linux section. So we do need to run this installation here. And then we're going to want to do the cloning of the Trelis LeRobot or the standard LeRobot. So I need to close and reopen the shell. So I'll just close that. And now I need to run these installs. So and with that, we should be able to go into the train act. So we should be able to run now with training. And what I can do is I can go back to my local implementation here. By the way, that training is done and the model is being pushed up to hub. So everything worked. And I was right to say that you should set this save checkpoint to true. Let's just check what that data looked like. If you go to LeRobot, then the outputs folder, which should be here, you can see now under train, we have act test and we have checkpoints. So yeah, you do actually need to set this here to true. I'm not sure this is correct. I'm going to just put in that might be questionable. Okay. Now I've made a few little changes here in data prep. So I'm going to push these up. And this I can actually comment out. So I'm going to just push these up to hub. I've made a small change in train. This is fine. I'll push this up as well. So anybody working on this will have the same parameters. And I'll sync these. And what this just means is now if I go across to the remote instance on the GPU, I'm gonna do git pull and just make sure that we have the latest version that's matching everything else. So you can see now on the remote, I've cloned LeRobot from Trelis. And we're currently running the installs that are necessary with the help of UV, which should be a little bit quicker. If I really want, I can just open up a new terminal here to git pull. And it should pull down some updates. Looks good. And if we go back to the installs here, it's updating Torch and CUDA to the required versions. And yeah, we can also sync the changes here to LeRobot. All right, so now we're going to run training on CUDA. So yeah, you can change this to CUDA and we can run the exact same thing. Let's actually go through this. It should tell me to log into weights and biases, I think. Actually, this should also fail because I need to log into Hugging Face. It's probably not going to fail because, oh, interesting. So we did hit a WebSockets issue here. That's not a problem. We can just do vpip install WebSockets. I have seen that issue before. And now let's try and run. Really, we should log into Hugging Face, which you can do with Hugging Face -cli and then log in. So I could get a token and log in there. My dataset is public though, so it should be fine. But it will hit an issue when I try to upload. So you do need to log into Hugging Face if you want to do this part. Now, let's just try the first part and see if it gets us to log into weights and biases. Yeah. So here it says weights and biases, enter your choice. This is not, I don't know how you're supposed to know, but put in 1 and it should tell you to put in an API key from your profile. And actually, if you check here on weights and biases, you can find a link that'll bring you to authorizing weights and biases like this. Now I need to just enter again here. I might be logged in, I might not be. Okay. I'm going to log into weights and biases and copy this code here. Paste it in and we're logged into weights and biases. And this is going to run a really short training because that's the parameters that I've set in train.py. So if you go here, it's going to run a really short number of, just like a few steps. Now, it looks like we have hit an issue here on CUDA. And let me check why that would be the case. So what I'm going to do is make use of cursor to see if we can fix this, diagnose the issue with training on CUDA. I don't immediately see what the issue would be here. I can check if there's anything to do with. I wonder if there's batch size issues, just because the total number of steps so I do need to remove this. Let's just see if this solves it. I don't actually think this is, it's interesting that this is not an issue on Mac, but it is an issue on CUDA. So let's see what cursor recommends. Now here we're actually not running. Yeah, we are still running into that issue. It's printing out currently. It's checking the version of Torch and CUDA that we're using. And I'm not sure we can try checking what. Yeah, it seems to be an issue to do with the validation set. As to why exactly that would be the case. So batch size of 1, 50 steps. Oh, really? No, that's not going to be the issue. Like this here, I can close. I can maybe start a new. I don't think that's the issue. Okay. Yeah, I need to pass this back in. I think I didn't pass the details of the error. Yeah, I suspect it's something to do with validation set. It's interesting that it's just coming up as an issue on CUDA, because I do have this data set here. I'm going to try this other data set that I know I have, which is a larger data set, and we can see if that causes the issue. Yeah, so it's a data set issue. Oh, it's not a data set issue. It's something else. So if we look here, I'm not entirely sure where this issue came from because I was previously running fine. It's making some updates here. Not entirely sure. So I do need to delete the old file. It's been saved. Yeah, okay, so that worked. And you can see it very fast when you're training on CUDA. So you're able to get data very quickly. I'll just run this on a few more rows so you can see what's happening. So instead of running it, let's run this out for 1,500 rows. So we'll run for 1,500, eval every 100, well, 200, let's say 100, log every, let's just run that once more. This is training again as a reminder on, we're training on 16 rows. So it's a larger data set. You do have to remove the folder if you're going to start a new training. So that's why it keeps giving that error. Interesting. So yeah. Okay, I'm going to add. It seems like data sets, we're using a different data sets version that previously was causing issue. Let's add a succinct note to train act. Get that fix. So yeah, here we're up and running with weights and biases again. And let's just take a look at how that training is going. Just training on a small number of rows, 16 rows, not 16K. Yeah, you see my storage is getting full up because we're doing all these saves. And actually, maybe I'm getting it to save. Yeah, no, that's fine. It's only going to save once. So if we go to runs and we look at the act training, you can see, yeah, already we're basically not using the encoder. And this is validation. If we look at the validation loss, it's come down, but it's already, well, it's probably just not stable quite yet. We need to see a few more rows. And if we look here, yeah, you can see that we're just really not using the style encoder. And if you look at the train loss, it's going down and it's starting to flatten here. So yeah, this is the run I'm doing right now in green. So we should have, sorry, it's this run here. Currently at step 1000. That doesn't look right because if we're at step 1000, okay, it's done. Sorry, we were beyond step 1000. And let's just take a quick look at the validation loss. Yeah, I mean, I wouldn't say it's particularly stable here. when you include the KL divergence. It is kind of going down here. That's the KLD loss. Yeah, it's basically zero. There's no style encoder being used. And it's arguable whether we're really getting any further reduction here in the validation loss. And if we look at the training losses here, training loss is going down nicely, which is good. And the L1 loss is going down as well. So this here, as I said, it's a larger data set. Actually, let's just check. Did I run it on the larger data set? Let's check what the command was. Yeah, I did. I'm actually not entirely sure which data set this is. I'd have to go back and look carefully whether this is my high quality 16 data point data set. But the reason I wanted to show you on CUDA anyway is just to get this whole process working. I'm glad I did it because I hit that error. So that should be fixed now if you're cloning from these repos. And that kind of sums up how to use CUDA. It's a lot faster. Basically, if you're running to 50 steps, you're probably going to want to run, let's say they're 20 seconds on average. That means you've got 1,000 seconds worth of data. And if you've got 30 frames per second, that's 3,000 frames that you're training on. And if you're training on 3,000 frames and you want to sample them 10 times, that would be 30,000 steps. Or if you're doing batch 4, it would be then 7,500 steps. I've gone through my maths on that, but basically you need to figure out how many frames you have and then make sure you have 5 to 10 epochs. That's your starting point. And then your finishing point is to always check the validation loss. Make sure it's going down. If you see it flattening or going up, that means you probably didn't need to train for just quite as long as that. So that's pretty much it here on the CUDA. I'll push these updates now. Now that we've trained the model, I want to show you the results where we will evaluate its performance. And I'm going to show you some bad results and some good results and explain to you where this works and where it doesn't. The short summary is that ACT works well when you have training examples that pretty much exactly match your production rollout. If you want to cover a large range of operation, you're going to need to create a lot of data. So let me start by describing where I think it's going to perform well, and then we'll do some rollouts and see where it performs well. So because we trained, and I ran about, in this data set, I didn't show the full data set being prepared, but I made about 16 points. So I ran picking up the cube from here and placing it over here. I did not include data in the set for small variations. I didn't include data for picking the cube from here. I didn't include data for picking the cube on the side. I didn't include data for putting the cube outside the view of this camera here. So what we're going to see is the robot should perform quite well if I put it here or really close to here. It should be able to pick it up and place it over here. But once I start to try with the cube starting here, it's going to run into trouble. Now, the first thing you should do after you've run training is you should test the exact same scenarios as your training. So you should try and replicate the cube position of your training examples, pick one or two of them, and see if the robot is able to do that. And the best way to do that is, rather than running evaluate, first of all, we're going to go back up to replay. So we're going to run a script that's going to replay some of the training examples. So I'll find here robot.replay, and I'm just going to replay episode 0, just the first episode. And replay just does the motor movements. So it's not using the camera, it's not using the model. It's just replicating the motor movements of my training. So let me paste that in and run. And of course, it's just the follower robot that's going to move. So we should see it open because that's how I ran the episode. And now the robot is moving, and it's moving towards the brick, which I'm picking up. And what I'm going to do here is I'm going to kind of put the brick where it should be, and I'm not going to let it pick it up. So I'm just going to replicate really exactly where that brick should be. So the whole purpose here is I want to figure out where the brick should be so that I can now run it with the model, and it's basically replicating the exact same training episode. So now I'm going to go down and I'm going to evaluate the model on that starting point. So here we have training, here we have evaluate, and I'm going to evaluate the model that I've trained. So this is the model rolling out. Paste this in here. And we can check if we like to see the rerun screen. So here Sorry for the infinite mirror on the right, but we should see here the camera pop up. Okay, so it's working. It's moving straight away, which is great. And it should be replicating something very similar to training. So it's getting the cube, picking it up. Now, I'm not saying it'll be perfect. It may make a mistake, but broadly speaking, this is looking good. It's doing what it did in the train example. This is using the model. Now, is it going to let go of the brick? You know, not quite as smooth as the training example, but broadly speaking, it's working. And it's coming back here. So this is good, you know, not quite as smooth. And I haven't got ensembling turned on. I'll talk about that in a moment. But I'm rolling this out in evaluation mode, and it's more or less following the training example. It's doing something funny here where it's kind of jolting, but I think it will settle down towards the final position. Maybe it doesn't see the cube in the exact same position that it was in. And the episode is just timed out there. So I would call that a success. Now, let's try this again, but let's try it this time with the cube starting in a more difficult position. And let's see what it does. So I'm going to put it here. This is definitely more towards the middle than what it would have been during training. And I expect it's going to struggle. It may decide not even to move from the start because the image here and the image here is just perhaps so far outside its training example. So yeah, it's moving too far to the left. It hasn't seen any training like this. Here, it's now not really sure what to do. I don't know if it's going to try to close because it probably doesn't see the cube between the pincers. And something I want to highlight here is that it's operating on a series of 100 frames, which is, we're commanding the robot at about 30 frames per second. So 100 frames is, it's projecting sequences of about 3 seconds. So if I do tap the cube now into a position that it starts to recognize, it's then going to roll out that kind of series of 3 seconds. So within about 3 seconds, it might start to recover because it recognizes it. Now, it may also just time out. But here, okay, we ran out of time. So let's just keep going because I want to show you. Basically, I just restarted the script here, give it more time. It's fine that you don't start in the starting position because it still should recognize this frame. Maybe I'll make it a little more similar. Oh, it knocked it over. If it knocks it over, there's no way it's going to recognize that frame. Now, see how it's actually going back again? That makes sense because it sees a position that looks familiar to it. Now, the cube is not exactly where it thinks it should be, so it's still not recognizing. Now, the cube is behind the pincer, which is a position that it probably never sees in the data set, so that's kind of bad. But maybe if I take it away and put it back again, it might manage to recover. It's probably going to time out. Can we get it to recover? Okay, so probably there I'm in the right position and it misses it. It should go back again. And it's not like it's smart and figuring out, oh, I missed it, I should go back. It's just that the video that it's seeing is familiar with a point that's earlier in the sequence. So I'm not being very successful here, at least in picking it up, but I am being successful in explaining to you why it's not exactly picking it up, because basically this image that it's seeing right now, combined with the set of motor positions, this is not familiar. And to some degree, you can get into positions where it's never going to recover because the pincers are so far forward right now. I'm just randomly doing this, hoping it moves the pincers away, and then trying to put the cube back in a position where it might be useful. And you can see there are various degrees of cheating. So yeah, I mean, I can entirely cheat and I can try to put the cube between the pincers. Here it hasn't even properly closed on the pincers, but you know, it's maybe somewhat recognizing where the cube is. We've got the cube in the jar, kind of loosely realizing that now the task is complete, but its motor position's up here. This is not a position that it ever sees in the data set. So it's running into trouble. So this illustrates to you that if you want to train to be general and pick this cube up from here, from here, from here, from here, you need to train it on data. You probably need 10 points that vary around here. You probably need to have 10 points that vary around here, maybe points between. In fact, you may want to just train some data points that are staggered across like this. If you want to further generalize, you might want to orient the cube in a few different ways, like this. You may want to orient it this way, so it gets familiar with this. And you can see there's even this little bit of stickiness from a sticker here, and that potentially could make a difference depending on the orientation of this. Now, if you have enough data, if I had, for example, 10 data points here, maybe 100 data points going all the way to here, at that point during training, I might be able to turn on color jitter. So you can search here within the training loop to look for jitter. And let me just see if I can color, because there's a parameter here that we can set. Yeah, in fact, if you want to turn on image augmentations, which will add some jitter to the images here, which should make you more robust to lighting changes, which is probably an issue. Even if I've got a ring light behind the camera you're looking at me from, if I turned off that ring light, it may even make things fail. So if you have large enough data, you can add jitter, and that will randomize the images so that you will become more invariant. But I can warn you that if you do that with just, say, 16 rows of data like I did, you're probably just going to fail, because it's going to overfit to the jittered images and it's not going to recognize any of the real images. And so it's not going to know what to do. And you might find that your robot just stays stuck. Now, there's one other thing I'll talk about here, which is deciding the number of steps of rollout. When we trained, we had to choose the window we want to train on. Basically, for every image, every frame, and there's 30 frames per second, for every frame, we can make a prediction of, well, this is what happens during training. We pick a frame and we make a prediction over n number of future steps for the motors. So you can set n. N is set to 100 right now, so it's predicting 100 steps forward. Now, the more steps forward you predict, the more the motor and the robot knows about the future. It knows about the future trajectory, and this is probably good because it makes it robust. If you just show it 2 steps in the future, which is milliseconds, tens of milliseconds, that's going to be very jolty in terms of movement. So you want K to be large enough so that you're not just trying to make the model good at predicting the very next 1 or 2 motor steps. But you don't want it to be too large either, because if you make it too large, that's going to slow down your model. The more steps you try and predict at once, the slower the decoding is going to be, and that potentially is going to pose issues when you're trying to do the inference. So you want to have a value of K, the number of future steps, that's going to be not too long, not too short. So if you want to see where to set this, you can go to the training portion of the README here, or of the train.act.md, and just scroll up to find this section here on the act configuration, which sets the chunk size and also allows you to set the number of action steps. So we'll actually just go into that, and we can see if we go down to the number of the chunk size, it's currently set to 50. So that means the model is being trained to predict 50 steps. It's 30 frames per second, so that's about 1 2/3 seconds in the future. And we also have this parameter here, which is called action steps. And actually, for this last one I showed you, I changed this and started recording again. This was actually set to 50. So even though the model predicts 50 steps ahead, we only use 15, which is about half a second. And then we recompute the next 15. So if I move the cube within half a second, it's going to respond and it's going to adapt to the next projection. And the logic here is that it's good to train the model on a longer length so that it gets familiar with the challenge of predicting far out. But then actually we only use the nearer steps because those are the most accurate. And if we did roll out the full 50, which you can try, it might work, it's potentially going to start to diverge from where the robot actually is, because the motor positions will always be a little bit different than predicted. So that's why you try to set the chunk size large, but you actually only use some of those predicted chunks at every step, and then you recompute. Now, there's another mode here that you can use called ensembling. It's where you make a prediction much more frequently. And of course, you could just lower this value anyway. But rather than just predicting one step ahead, which would actually result in a very bumpy trajectory, than repredicting every time step, which would be difficult because you'd have to recompute literally every time step. And that still is difficult. It would also be potentially bumpy because you'd have a whole new prediction every single time step. What you can do is make the prediction every time step, but ensemble across those, weighting mostly the latest predictions and weighing less the older predictions. So you can imagine now every time step we've a new 50 predictions, but the older ones are expiring and we're weighing them less, and the newer ones we're giving heavier weight. And in fact, the way that weight drops off, we can set down here in the ensembling coefficient. It was set to none previously, and I've just set it now to 0.01. So I'm going to try now with ensembling, and you can tell me whether it's smoother than without using ensembling. This is the premise of ensembling. To get the cube position correct, I'm going to start by running, let me just check, I've put that in as 1. Yeah, that looks good. I'm going to start by going back, I've got another keyboard here, and doing a replay. Oops. Replay. Here we go. And I'll just replay the 0th episode. So the robot will jump back because it's going to... All right. Just replaying here. By the way, I am in the camera's view, which is bad for a training example, but it's fine now because we're just rolling out the motor position that I used during training. And I'm going to place the cube exactly where the robot expects it from the training example. And when it's done with this, I will do a rollout. So I'll evaluate the policy, but I'll evaluate it with the cube in that position, which should give it a very good chance. All right, so it's finished with replaying. Now we're running the policy. I'm going to get out of the way. Here's rerun. Make sure the chair is out of the way from the camera. Okay, that's good. And you can see here, it's moving down. You can decide whether it's smoother. Okay, it does grab it. Oh, it drops it. So potentially the ensembling is giving it some kind of an inaccuracy that wasn't there before. And we can see if it tries to recover. I think it's going to have a difficulty lifting it. Yeah. The ensembling in this case is actually making it less robust, not intuitive that it would. But I guess the noise it's introducing there by making frequent predictions is causing it to drop it. Maybe in that position. No. So that's an illustration of ensembling. Potentially it can give benefit. You kind of have to empirically test whether it will work. But it seems like, yeah, it's timed out. It seems like just taking the standard approach of rolling out for a portion of the total predicted steps is the most robust approach here. So you can see with the ACT robot, the whole approach involves overfitting the training data set more or less. You additionally have the issue of style, which I talked about in the second video. This is not much of an issue here because I trained it only using one style. So if you look at the training results, as I talked about, there basically is no multiple styles. So the encoder, you could probably just drop it, the style encoder in this case here. If you did train it with different styles, you should see that encoder comes into play, but it's not coming into play here because my data set is pretty simple. The next step will be to use a more general model that's been pre-trained, and hopefully that will be able to perform well with just a few simple fine tunes like the data set we have here. And that will be the subject of a future video. And that is it, folks, for this episode on training the ACT policy for the SO-101 robot. You can also train this policy for another robot if you have the Coke or the MOSFET one, for example, or some other branded robot that's compatible with LeRobot. In the next episode, I'm going to go through training a pre-trained model, which hopefully can generalize a bit better. We will even try it in zero shot with no training to see what happens. In the meantime, if you want to follow the earlier videos, you can find them in the robotics playlist here on the Trelis YouTube channel, and you can find the materials, the detailed guide at trellis.com/advanced robotics. That's TRELIS1L.com/advanced robotics. As usual, let me know your questions in the comments. Cheers.